If changing one field breaks ranking everywhere, your schema is doing more harm than good. We will design a simple search schema in Python that makes future tuning less scary. You probably see odd search results after a small change. Title drops below body matches. Tags dominate unrelated queries. After this video, you will be able to set up fields, choose simple analyzers, and assign weights so changes are predictable. That reduces surprise and speeds up iterations. I'm Professor Pi, teaching search and IR from basics to advanced, with simple, concepts-first Python that helps you solve bigger, real-world problems. Search schema design is about control. When you build a search system, you decide which parts of a document matter. Title, body, tags, and metadata all behave differently. If you treat them the same, you get noisy relevance. Treating them carefully gives you faster improvements than swapping ranking models. In practice, this is a pipeline decision. The schema stage sits between raw text and scoring. It decides how text becomes terms and how much each field influences the score. Good design helps on small data and larger indexes of tens of thousands of documents. It also limits regressions when you tune later. At a high level, there are three levers: fields, analyzers, and weights. Fields are the buckets for text. Analyzers turn text into searchable tokens. Weights tell the ranker which fields should weigh more. Imagine a product page. A match in the title should usually outrank a match in a long description. That instinct is what we try to encode. We will use a tiny corpus with a couple of documents. We keep the example consistent so you can reason about changes. The goal is not a production-ready engine. It is a clear recipe that shows how a simple analyzer and a few weights change decisions. This prepares you to scale or replace components later. Now we will set up a tiny corpus and a basic analyzer. This snippet sets up a tiny corpus and a basic analyzer. We define docs as a list with one record that has title, body, and tags fields, so we can reason about per field behavior. The function talk lowercases and splits on word boundaries to simulate a simple analyzer. We then count tokens in the title, body, and tags of the first document to see how raw text becomes terms. The counts show field-specific tokenization and give a baseline before any further processing. The printed token counts confirm the schema's fields are being parsed consistently. Next, we will make the analyzer stop-word aware for the body field. This snippet introduces a stop-word-aware analyzer for the body field. The variable stop holds common function words that add little meaning for ranking. We redefine tonk to filter those words after lowercasing and tokenizing, keeping only informative terms. We then apply toke to the body of the first document and join the remaining terms to show what will be indexed. Expanding the stop list removes more clutter and can improve precision, while shrinking it tends to increase recall. The printed body terms show which tokens survive the analyzer and will carry weight in scoring. Now we will add a second document and test a simple overlap ranker. This snippet adds a second document and ranks with term overlap. The variable q holds the query, and we append a new record that includes the phrase green T so we can evaluate retrieval. The set TQ contains unique query terms for fast membership checks. We score each document by counting how many tokens across title, body, and tags match TQ. Then sort by score and break ties by ID for stability. This simple overlap baseline exposes whether fields are being read and combined correctly. The printed rank shows the document order driven purely by matched terms. Next, we will assign explicit per-field weights to steer relevance. This snippet adds per-field weights to control influence in scoring. The dictionary W encodes our schema intent. Title terms matter most, body next, tags least. The function score multiplies term matches in each field by its weight and sums the contributions, producing a single value per document. We select the best document using max with a stable tiebreaker on ID. Increasing the title weight sharpens head term precision, while raising body weight tends to stabilize recall for broader queries. The printed weighted ID and score show how the schema changes the decision boundary. Finally, we will boost exact title phrases to favor precise navigational queries. This snippet boosts exact title phrases to mimic a phrase analyzer. The variable phrase is built from query tokens, and P checks whether the title contains that exact sequence. We add a boost to the weighted score when P is true, creating a tiny hybrid that respects both bag of words relevance and phrase precision. The list HB holds combined scores, and top selects the best with a stable tiebreaker. Increasing boost emphasizes exact phrases and can improve precision on navigational or specific queries. Decreasing it softens the effect. The printed hybrid ID and score show the phrase-aware win. This toy flow maps directly into a real system. The tiny corpus is your unit test. The analyzer choices become index time settings. The weights are the schema file you store in version control. When you change a weight, you can replay a small test set to verify behavior before pushing to production. Quick recap. What it is: a simple schema using fields, a basic analyzer, and per field weights. When to use it: when you want predictable, interpretable ranking changes fast. One caveat: this is a simple model. Modern systems add term frequency, IDF, and phrase models that shift absolute scores but not the core schema logic. Next step: pick one parameter to tune. For example, increase the title weight and measure how many test queries flip top results. That focused experiment gives immediate signal about schema sensitivity. If short practical IR helps, subscribe and watch the IR videos.